Welcome everybody to ME3501 lab. This is the first lab of the semester, and today we're going to be talking about the resistance strain gauge, which is one of the most important devices that we use to measure both displacements and forces and pressures and so forth. In fact, in this lab alone, you're going to encounter the strain gauge explicitly in 2 of your experiments, and you're going to be using devices that utilize strain gauges to measure forces in another 2 of your experiments. So this is a very important device. As a general rule, when we're trying to measure forces, we have several techniques available to us. Like, for example, if you have a balance beam, then what you're doing is you're putting an unknown weight in one side of it, and you're putting known weights on the other side of it, and when the 2 of them balance out, then you deduce the weight of this side. So you can measure forces by comparing them to a known force. The other common technique that we use to measure forces is to apply the force to a deformable body, to a spring. And then if you know the cross-section of the spring, and you know the modulus, and you know your strength of materials theory, then you can calculate for a given applied force or moment or torque how much that deformable body is going to deflect. So if you measure the deflection of the deformable body, you can deduce what the force was that was applied. And that's the theory that we're going to be using in the measurement of the strains that we are going to have on our cantilever beam today. And then later on in the lab, you're going to use a complex set of loads that you apply to a tube that is being deflected both in bending and in torsion, and then you'll measure a complex state of strain on that one using a strain gauge rosette. And in our experiments where we do tension tests and the experiment where we do torsion, the load cells, the devices that actually measure the tensile force, as well as the device that measures the torque that you apply to your torsion specimen, also use resistance strain gauges. So these are objects that we use in the lab a lot. It's a good thing for you to become familiar with them. If you end up doing experimental stress analysis, you will also be using these strain gauges very commonly out in the field. So just to give you a quick example of that, back around 1996 or something, I was doing a large failure analysis investigation that involved the failure of truck axles. One of the largest manufacturers of tractor trailers in the United States, called Utility Trailer, had just switched the suspension on their trailers from a standard leaf spring to what was called an air ride suspension, where essentially instead of the spring you have a gigantic rubber balloon that you put in there as your spring between your wheels and your chassis. And the advantage of the air ride is that because the rubber balloon compresses a long way compared to the relatively stiff leaf spring, you get a softer ride. So your objects which are fragile, if they're in the back of the truck, if you go over a pothole, they don't shatter. So that was the reason that they switched to this air ride. Plus it's an adjustable stiffness. You can, by changing the air pressure inside that rubber balloon, you can get a stiffer ride or a softer ride. So it's got a lot of advantages. The disadvantages of the air ride are that if you have a more compliant spring, that means when you go over a pothole, your wheels move more. And so as a result of that change, there were some unanticipated problems. Namely, there was fatigue failures of their truck axles. And you know, you don't want to be traveling down the freeway and a truck axle breaks and you have a dually traveling down the freeway at 70 miles an hour hitting cars. So we were doing an analysis of why it was that those truck axles were failing. And in order to get real world data, you can do all the modeling that you like, but unless you have high quality data about what forces the axle is actually encountering, your analysis is not worth very much. So as part of our attempt to get real life data for what stresses those truck axles were experiencing in the field, we instrumented the truck axles and the suspension with strain gauges of just the exact type that I'm going to be talking to you about today. And then you put a data acquisition system on board the truck and you drive it down the freeway, and then you pick up all of the different kinds of loads that the axle encounters, just from regular road roughness to occasional potholes to curbing loads. If you hit a sidewalk or something like that, braking loads, all of those things get captured in that real world data. So these strain gauges get used all the time. Now, how do these strain gauges work? If you take a look at just a straight piece of wire that has length L and cross-sectional area A, hopefully you remember from your physics or from your electricity and magnetism or a circuits class, that the resistance of this little piece of conductive wire is proportional to the length and inversely proportional to the area. In other words, if I make this thing longer and thinner, then the resistance will increase because the length gets bigger and the area gets smaller. If I make it shorter and fatter, then the resistance will drop. So if I take a little piece of plastic over here and I put a piece of wire on that that winds backwards and forwards like this in a particular direction, this object now is quite sensitive in terms of the resistance of the device, is quite sensitive to deformations in this direction. Because if I stretch it this way, then all of those little wire segments are getting longer and thinner. But it's quite insensitive to deformations in this direction, because if I stretch it this way, all that happens is essentially the loop opens up like this, which is very small effect on the resistance. So this is a highly specific device as far as the directionality goes for measuring the deformation of the underlying material. So what we do is we take a little piece of plastic that has these wires bonded to it, and we glue that onto the surface of our material, and that's your strain gauge. And then you take leads and you attach those leads to these two pads, and then by measuring the change in resistance of the wires, you can measure the deformation of the underlying material. And there is a quantity called a gauge factor that is associated with each one of these pads, which is related to the design of the specific strain gauge, which tells you for a given change in the length per original length, this is the engineering strain, change in length per original length. So if I have a certain amount of change in the length of the material per original length, how much change in resistance do I get in the strain gauge? And these gauge factors typically are around 1, 2, depends on the design of the strain gauge. In this lab, most of our gauge factors are somewhere around 2. And when you buy a package of strain gauges, it comes with a little calibration sheet that tells you exactly what that gauge factor is. So now I have this gauge factor. I want to measure the change in the resistance of my strain gauge so that I can figure out how much my material stretched, right? In other words, if I figure out the change in the resistance, and then I take this object over here and divide it by the gauge factor, that gives me the strain, which is what I'm looking for. Now, one thing you could do is I could just have a inline element like this, which is in tension, put my strain gauge on there, I put a load on it, and then I measure the change in resistance over here. If you do that, you're going to have a very small change in resistance, because most materials that you would be mounting this strain gauge to, including metals and ceramics, have very small elastic ranges, right? So if you remember from your strength of material, if you take a piece of steel and you apply loads to it, the strain that you can go to before you start getting plastic deformation is only like 0.5% or so. So if I have 0.5% of stretch on this thing, then I'm going to get 0.5% or maybe 1% change in the resistance. And and that's going all the way to the plastic limit, to the yield strength. If I have a smaller deformation, which is what you typically have during normal loads that are applied to a structural member, then you'd have even less than that. So let's say I have 0.1% strain, which is a typical elastic strain. That's actually a fairly large elastic strain for most structural members that are made out of metals. And if I have a 0.1% strain, and this is in tension, then if my original resistance was 100, if my gauge factor is 2, then if I have a 1.1% strain, then my change in resistance is going to be 0.2 ohms, right? Gauge factor of 2 times 0.1 ohms. And so my total resistance is going to be 100.2 ohms. Now, if I'm just measuring this resistance straight with an ohm meter, that poses a problem for me, right? Because what that means is I now have already 4 digits in my resistance over here. And if I want to measure this change accurately, like let's say to 1 part in 100, that means I would have to have 6 significant figures of accuracy on my ohm meter to measure this change to 3 digits, right? And it's extraordinarily difficult to make an ohm meter that is that stable and that accurate to 6 digits. So instead of just measuring the resistance straight up like that, we look for ways to magnify that difference in resistance. Okay, and there's ways that you can magnify the difference in resistance mechanically, and ways that you can magnify the difference in resistance electrically. Mechanically, what we want to do is, if for the same force, we want to generate a larger displacement in the material, and that will give us a bigger signal to measure. So in the load cells on our testing machines, what you will see is that inside the load cell, they don't have just a straight tensile member. They'll have a beam that is bent like this with strain gauges on the top and the bottom. And then essentially when you apply the same load, this thing is just going to stretch directly in tension. But here you have a bending moment that has a mechanical advantage basically of this cross-section divided by that length, right? So the bending moment in this object over here is going to be bigger by this divided by that ratio. And so you're going to get a much bigger displacement or strain on these 2 strain gauges that you put on the top and the bottom of the beam than you would have gotten on a straight tensile member. So typically in load cells, you'll find arrangements like this designed to create a larger strain signal per load than you would get in a straight member. The way that you can magnify this difference electrically is by using something called a Wheatstone Bridge. And this is implemented in all of the strain gauge readouts that we use in this lab. And essentially what a Wheatstone Bridge is that you have this diamond-shaped arrangement of 4 resistances, all of which are supposed to be nominally the same. So if your resistance strain gauge has a standard undeformed resistance of 100 ohms, then your resistances over here are also going to be 100 ohms. And then you apply a DC voltage using a battery or else a DC power supply to the top and bottom of this diamond shape, and you read out a voltage across these 2 nodes over here. So if these resistances are all exactly identical, then the voltage drop across this and across that is exactly the same. Here and here, those voltage drops are exactly the same. So when I read the voltage across these 2 points, I should get 0, right? So if these are all exactly identical, I'll get 0. So now, if you put your resistance strain gauge as one of these 4 resistors, now I have a single active resistance over here, and the other 3 are dummies. This is called a quarter bridge configuration. And now I deform my object, and the resistance of this one varies a little. When the resistance of this one varies, that means this voltage goes up or down a little bit, right? If I make this resistance a little bit larger, then the voltage drop here will be bigger than that voltage drop, and this side will go down. relative to that side as far as the voltage is concerned. If I make this resistance smaller, then the voltage drop here will be smaller relative to that one, and this voltage will go up relative to that one. So now, the nice thing about that is that instead of trying to read the change in resistance directly, starting from a large value on which this change in resistance is a small perturbation, which requires you to have a lot of significant figures on your readout. Instead, you're starting on this voltage reading over here from 0. And even if you have a really tiny change in the voltage, well, you can just increase the gain on your voltmeter and you pick up just the difference, not the difference plus some big starting value. Since you're starting from 0, it's a lot easier to read that. So that's the whole point of this Wheatstone Bridge. Now, in this particular experiment, what we're going to be doing is we're going to be setting up 2 different setups, and they have advantages and disadvantages. The simplest setup you can use is what's called a quarter bridge, where you have 3 dummy resistors and 1 active resistance. And this is the setup that is used most of the time when you're trying to get the largest number of data channels out of your data acquisition system, because it just requires a single reading over here to give you the strain. If you have more than 1 active resistor, active gauge over here in your Wheatstone Bridge, that increases the sensitivity of the system, and it helps you reject certain kinds of systematic error at the cost of greater complication and greater electronic overhead in your devices. So one alternative to this quarter bridge, which is not super duper sensitive, but which is very simple and efficient as far as the usage of the electronics, is a half bridge, where you have, in our case, what we're going to be doing is our cantilever beam over here is fixed on one end, and then we are going to be applying an end load to the cantilever beam, and then we're going to try to measure the strains at the top and bottom of the beam, and we'll put 1 strain gauge at the top very near the support over here. If I just use this 1 strain gauge, then in this configuration, then that's going to have the sensitivity of this single gauge setup. That's the quarter bridge setup. But I can also have another resistance strain gauge on the bottom of it, and that would be this half bridge setup, where this one is the top, this one is the bottom. And now, as I bend this thing, the top stretches, the bottom contracts, so I get double the motion of the voltage over here, because this resistance is getting larger as you stretch the top. This resistance is getting smaller as you compress the bottom, so I get twice the change in the voltage as a result of this half bridge setup than I would have gotten in the quarter bridge setup. And if you want to get even more sensitivity out of it, you can have what's called a full bridge, where you have 2 resistances at the top. So I would have 2 separate resistances, both. This is not shown, like I'm not showing the full top surface, but if I drew the full top surface, I would have 1 resistance here, another one in the same longitudinal location, just moved sideways, and that would be this one and this one. And then for this one, I would have the 2 compressions, and that would be this one and this one. And then that way, as you deform the bridge, this one goes down double, this one goes up double, and you get quadruple the change in voltage as a result of the deformation of the deforming beam over there. So we're not going to do the full bridge in the experiment that I'm going to show you. We're going to do the half bridge with 2 active gauges. We're going to do the half bridge with 1 active gauge and 1 resistance strain gauge that is on just a chunk of metal. And then we're also going to do an experiment with a quarter bridge, okay? And then when you do the experiment later on in the semester, where you're measuring a strain gauge rosette to measure complex deformations of a beam and combined bending and torsion, you're going to use 3 of these quarter bridge setups to measure the 3 strains in the rosette. For this simple setup over here, we're going to use one setup which is just quarter bridge, one setup where we have 2 active strain gauges, and then a third setup where we have 1 active strain gauge and then a strain gauge glued to a piece of steel which is just sitting on the side. Now the advantages of this quarter bridge and the half bridge with the 2 active gauges by now should be obvious to you, right? So this is twice as sensitive, so you get a more accurate measurement of your strain. There's another advantage of this half-bridge setup though, which is what I'm really trying to do, and in this experiment with the beam and bending, is to pick up the bending strains, right? So, but this object might have things on it other than bending strains. Like for example, let's suppose that it's also undergoing tension and compression. Or let's suppose that I glue these things on when the lab is 70 degrees Fahrenheit, and then I do my experiment when the lab is 80 degrees Fahrenheit, and then I might have thermal expansion, right? So it would be nice if my experimental setup rejected the things that I don't want to measure and measured only the thing that I do want to measure. Right? Now if I'm just using the quarter bridge setup over here, I just have 1 active gauge at the top. That active gauge is going to respond to all 3 of those factors that I told you. If I bend it, it'll show a change in resistance. If I stretch it, it'll show a change in resistance. And if there's thermal expansion, it will also show a change in resistance, right? So it's not rejecting any of those modes. If I have the 2 active gauges, 1 on top, 1 on the bottom, remember the way this is set up now is this, when this one stretches, the voltage over here goes down. When this one stretches, the voltage over here goes up. Right? So that's why I put this one on the bottom of the beam and this one on the top of the beam. When the beam bends, this one stretches, that one compresses. Right? So this one stretches, the resistance gets bigger. This one compresses, the resistance gets smaller. Both of those end up lowering the voltage at this node. Right? So they cooperate to read the bending deformation. What about those other 2 deformations that we talked about? Well, if I have thermal expansion, both of these are stretching. Right? So what that means is that this one increases in resistance, but this one also increases in resistance. And that means that this is still going to be exactly the halfway point between these 2. So the fact that I have a positive and a negative strain gauge over here, both getting stretched, cancels that out, and I still read 0. So essentially this setup rejects the thermal expansion strain, and you don't read it. Same thing with tension on compression. If I had tension or compression, if I had tension, both of them would get stretched. That would get nullified. If I had compression, both of them would get compressed. That would get nullified. So the only thing that this thing picks up is the deformation mode where this one is getting stretched, that's getting compressed, or this is getting compressed, that's getting stretched. In other words, bending, right? So that's another cool advantage of the half-bridge setup, is it compensates or rejects the modes of deformation that you're not interested in. Now, the third setup that we're going to be using in this experiment, where we have one active gauge actually attached to the object, and then the other active gauge is attached just to a block of steel, that has some advantages and disadvantages of both setups. It has the advantage that it rejects thermal expansion, because presuming that you glued this onto your beam at the same time that you glued the other strain gauge onto your little block of floating steel, if this one expands thermally, this one will also expand thermally, and you get the same. If I put them in this configuration over here, the thermal expansion will get nulled out. However, since I only have one of my two gauges actually attached to the object, the sensitivity of the reading is just a quarter bridge sensitivity. So in the one where we have one on the beam and one just sitting on a dummy block, you get the same readout sensitivity as the quarter bridge, but the thing that you gain for your added complication is you will now not have to factor in the thermal expansion, which in this particular lab is not a big deal because we're operating at room temperature anyway. But if you were instrumenting the device for travel across roads, let's say, and you put the strain gauges on in the garage of your laboratory, and then you're traveling to Minnesota and you're traveling to Arizona, then compensating for the thermal expansion is a valuable thing potentially. In most cases, if you're interested in automatically rejecting thermal expansion, though, you would do a full two active gauge half bridge setup, or else a full bridge setup, so that you're getting the full benefits of increased sensitivity as well as the rejection of the thermal expansion. Okay, so that's enough talk about strain gauges. Why don't we move on over to the cantilever beam experiment, and we'll do a run through, and then we'll provide you with the data from the experiment so that you can do the analysis where, for given loads at the end of the cantilever beam, you can, using strength of materials theory, calculate the moments that are applied at that point. And when you know the cross-section of the beam, you can calculate the experimental strains that you would encounter there, and you can compare that to the experimentally measured strains. Or alternatively, from the experimentally measured strains, you can calculate the moments and then compare them to the theoretical moments that you would get from your strength of materials calculation. So let's go over there, and then we'll show you how the experiment works.